And what we're going to see is that they overestimated the resisting strength and they underestimated the driving forces, a fatal combination of misestimation. Well, let's look at the shear strength. This particular chart is from the original design document, and I apologize for its quality, but here we have the levee fill, the marsh soils, the clay, and the sand, and what we have is a strength of, as a plot of shear strength in tons per square foot versus elevation in feet, and each one of these little dots is its own particular test. Let's take a look at the soft clay for a minute. This is a blow-up, and this is the envelope that was used for design. In other words, that's the soil strength that the engineers said was available to resist failure. But the curious thing is that most of the tests fall to the left of that or weaker than that. So I would contend, Dr. Elton would agree, that the designers were a little bit optimistic on soil strengths that they decided to use. They made another crucial error. Remember, these levees have been in place for a long time because they were there as part of the flood protection system. And when it came time to build the eye walls, the Corps needed information, so they went out and they did soil drilling. And they always drilled from the crest of the levees most of the time because right down here, there were houses built right up next to the levees. And people don't like drill rigs in their backyard. Drill rigs are very messy. This is the canal site over here. And one thing that we know about normally consolidated clay is that as the weight of overburden goes up, the strength of the clay goes up, usually in a linear fashion. And so a soil sample taken at B has overburden from the levee and its natural overburden, and that's going to lead to a particular strength. But A doesn't have that overburden from the levee, yet the designers assumed that A and B had equal strength, and in fact, the strength at A, which we need to resist failure, was very much lower. So we have another reason that the shear strength was greatly overestimated in our stability analysis. Then, forces acting on it. The designers assumed that this water-filled gap would not occur, and the only hydrostatic loading would be on the concrete part of the wall. Well, in fact, what happened is that as the water came up, the wall tilted just a little bit, and it doesn't take very much of wall movement to open up a very narrow crack that allowed full hydrostatic pressure to develop on the wall. And what we had happening then was in their slope stability analysis, they had greatly underestimated the forces acting to cause failure. Well, the combination of those two things leads to this particular situation. If we use the right soil strength and we use full hydrostatic, then we get a factor of safety of 1, or failure. And that's really what we should have gotten. There's a couple other things of real interest here, too. For one thing, remember the old circle on that previous slide went underneath the wall, and it actually engaged this part of the embankment, which was providing additional shearing resistance. But what we've done is essentially sliced the cake in half. And so we've lost all of the shearing resistance on the upstream basis by virtue of having that crack, that gap, open up. Another thing we ought to point out here too is this is kind of some unusual geometry. There's a little step function there, as you can see, and it so happens that they cut this material out during the eye wall construction, and the reason they did that is that they were concerned about failure into the canal. So they were sophisticated enough to be concerned about the stability, although I think if you look at it, there's really no driving forces for failure into the canal, unless you want to consider some sort of rapid drawdown situation, which may have occurred. But so they had done some critical thinking about stability, but they totally missed how this was going to behave on the protected side at 17th Street. And if we look at the further evidence, we have a failure in the clay, which is overlain by marsh soils. If this is our failure plane, we get the clay moving up into the marsh. And in fact, that's what you can see right here. Here's a layer of clay that's been pushed up into the marsh soil. This would be the failure plane right at the bottom of the clay here. And the Corps did, in fact, age date both of those layers of marsh to assure ourselves that clay had, in fact, been pushed up in there by the failure plane. Well, let's go to London Avenue, which was a different set of geologic conditions. At London Avenue, we had levee embankment, overlying marsh soils, a thin layer of marsh soils, but instead of clay, we had sand. It was very dense at London Avenue South because it was an old beach sand, and in its geologic past, it had been pounded by waves. And so it was very dense at London Avenue South, right here, and very loose at London Avenue North because that sand was on the other side, not subject to being pounded by waves. And so we have very different failures that occurred. This was really a blowout failure, and here we had a much larger failure, which was probably much more of a slope stability failure. Here the analysis wasn't shear strength. Here the analysis was design flow net, and I think if any one of you submitted this to Dr. Elton, you'd be back doing it at home again. This is a very, very poor flow net, and he'll tell us why after this lecture. But if you do design with a good flow net, flow nets are very good tools. You find that the factor of safety is about, and this is against a under seepage type failure, is right around 1 with no water filled gap, and drops considerably below 1 with a water filled gap. And in fact, that's what happens. The wall deflected just enough to allow that water filled gap to open, and it brought full pool hydrostatic immediately under it. And what happened at London Avenue South, the very dense sand literally blew a hole through the marsh soils and was really a classic under seepage failure. At London Avenue North, it was probably much less dramatic under seepage type failure, but the loss of section allowed it to become more of a slope stability type failure at London Avenue North. But nevertheless, stuff happens, and this is just one photograph of the sand that was blown out of these failure areas, and that sand extended for blocks and blocks into people's homes, over people's cars. It was an amazing failure. Well, there were a lot of other contributing causes to these failures that we have to take into account. Probably the biggest one was that the hurricane protection system was a system in name only. It was really a series of agglomerated projects that were stuck together. And there was no systemic view of how it should behave. There were broader protection strategies that were blocked by the court or by local opposition. The Corps wanted to build gated structures at the mouths of those 3 outfall canals, but they were blocked from doing so, and rather than fight it, they gave up and said, okay, we'll go to Plan B, which are the flood walls, and you see how they behaved. Clearly, there were questionable land use decisions that allowed people to build in vulnerable areas more than 10 feet below sea level. One of the worst things was that the management of this hurricane protection system was completely chaotic and dysfunctional. There are about 7 or 8 individual levee boards in the New Orleans area, each responsible for a piece of that hurricane protection system. They did not work together. The levee boards did not care about critical life safety. They cared about marinas, airports, other kinds of activities, and the levees and levee safety really took a back seat. So this multiplicity of jurisdictions didn't work together, and they certainly didn't have anybody that was in charge, and that really contributed to the fact that the system was not a system. These levee boards are also responsible for 30% of the funding. They wanted to cut costs at each step of the way, and that pressure ended up compromising safety. And surprisingly, part of the reason was the levee boards, but part of the reasons was the system itself. There were holes in the system, penetrations, that were just left open during the storm. Hundreds of penetrations. Some of them were gated structures where the gates didn't work. And these penetrations were for roadways, railroads, pipelines, any number of features that have to penetrate a levee or a flood wall, but they were unfortunately left open. Here's one of the more egregious examples, and this is probably a little bit difficult to fully comprehend, but let me try and explain. Here, this earth berm here is in fact an earth levee. At this point where it failed, normally it would have made a 90-degree turn and tied into this eye wall, which goes across here and continues on. And so we had it's a fairly complex system, but you can't really turn and make that cut because we got this railroad here. And we also have this gate over here. There was a gate which was closed, but in fact, you can see how big an opening is where water was just allowed to flow through that. I mean, we have a levee here and an eye wall here and a big hole in between. And this is another shot of the same thing. And that yellow line is the same one. So that would have been the design levee height. Look at how much space there was for water to flow through here. And here's an incredible thing too. Here's the gate right here. That's the main roadway. Somebody said, well, you know, I guess we want to go, if the gate's closed, we got to be able to still get around it. So they built a road around it, right here. See that road? And look at how much lower it is. And then recognize that that ballast that the railroad tracks are sitting on is incredibly porous. So a lot of water moved through that as well. So we have just this huge hole that contributed to the flooding. And unfortunately, this doesn't show up, but see that little seal on that car right there? You know what it says? It says Orleans Levee Board. I mean, these guys were driving that every day and saying, you know, well, we got an eye wall on one side and we got an earth levee on the other side. Why don't they connect? All right, more contributing causes. Most of the levees were constructed, well, they were 2 feet too low. Some were constructed 2 feet too low, and others sunk that way due to subsidence in New Orleans, and some had a combination of it. But you know, I don't know if I didn't mention on that earlier slide, the levee system was supposed to be in the range of 12 to 15 feet above mean sea level, and it's 2 feet too low. That's a lot of delta that, had it been there, would have really knocked a lot of Katrina's surge off. You've seen that the margin of safety was really too low at each step of the way, and that was allowed because there wasn't really any independent review. The pumping system was actually designed for rainfall events, and for safety reasons, they abandoned the pump station, so it was useless during Katrina. And then Katrina itself flooded the pumping station, so it was weeks of repair before they could be put back into use. We had a 40-year construction project for a critical life safety system, left some sections too low, some sections incomplete, and risk was never, ever communicated in New Orleans. And at the end of the day, by omission or commission, the hurricane protection system was simply not considered a critical life safety system.